Hello everyone. Today me and my teammates are going to discuss a mini project on BCD counter. Myself Janavi MS and my teammates are Aditi Sunil Warrior, Aishwarya N and Jyotika R. Let us see what are the contents we have to study in this session is Introduction to BCD counter, structure of BCD counter, operation of BCD counter, advantages of BCD counter, limitations of BCD counter, applications of BCD counter, design consideration for BCD counter, troubleshooting BCD counter, future developments in BCD counter, program code and output and conclusion. Let us see Introduction to BCD counter. A BCD counter is a binary coded decimal counter that counts in decimal digits. It is commonly used in digital systems to display and count decimal numbers. BCD counters are designed to count from 0 to 9 in binary form. Structure of a BCD counter. A BCD counter typically consists of 4 flip-flops, one for each decimal digit 0 to 9. Each flip-flop represents a single digit in the BCD count. The outputs of the flip-flops are connected to BCD to 7 segments decoded to display the count. Operation of BCD counter. When the BCD counter is reset, all flip-flops are set to 0, displaying 0000 and the 7th segment display. With each clock pulse, the count increments by 1 following the binary coded decimal sequence is 0 to 9. The BCD counter resets back to 0 after reaching 9 and starts counting again. Now my presentation is handed over to Aishwarya N.
Hello everyone, today I am going to explain about the advantages of BCD counter. BCD counters are easy to interface with 7 segment displays for visual representation of the count. They provide a simple and efficient way to count in decimal form using binary logic. BCD counters are widely used in digital clocks, calculators and other devices requiring decimal counting. Limitations of BCD counter. BCD counters are less efficient in terms of circuit complexity compared to binary counters. They require additional logic to handle the BCD to binary conversion for arithmetic operations. BCD counters may have limited scalability for counting beyond single digit decimal numbers. Applications of BCD counter. BCD counters are commonly used in digital clocks to display hours, minutes, and seconds. They are also employed in calculators for performing arithmetic operations in decimal form. BCD counters find application in industrial automation, process control, and electronic instrumentation.
Now I am going to discuss about design consideration for BCD counter. Careful design is required to ensure proper synchronization and glitch-free operation of the BCD counter. Signal propagation delays and setup times must be taken into account to prevent timing issues. The choice of flip-flops, clock frequency, and decoder logic impacts the performance of BCD counter. Next, troubleshooting BCD counter. Common issues with BCD counters include improper clocking, race conditions, and faulty connections. Troubleshooting techniques involve checking the clock signal, verifying flip-flop outputs, and testing the decoder circuit. Simulation tools and logic analyzers can hide identifying and resolving problems with BCD counter. Next, future developments in BCD counter technology. Adv- Advancements in integrated circuit design are leading to more compact and efficient BCD counter implementations. Integration of BCD counters with microcontrollers and the programmable logic devices offers enhanced functionality and flexibility. Research is ongoing to improve the speed, power, efficiency, and reliability of BCD counter circuits for diverse applications. Thank you.
I am Aditi Sunilware and I'm here to explain the program code. So basically the module BCD counter has two inputs, the CLK which is clock, reset, and one output which is Q. Q is a 4-bit BCD binary coded decimal counter. So inside this module there is a 4-bit register T. This T acts as a temporary storage for counting. The always block triggers on the positive edge of the clock signal, which is given by pos edge CLK. So if we look at the reset signal, if the reset signal is asserted, the counter is reset to 0. Otherwise, on each clock cycle, the T register is incremented by 1. When T reaches the value 9, that is, if T is equal to 9, it wraps around to 0 to implement a BCD counter. The BCD value stored in T is then assigned to the output Q. This is the end of the code. Look at this output. It is a 4-bit BCD counter sequence counting from 0 to 9 repeatedly. So how it works is that initially the reset signal is asserted, which sets T and Q equal to 0. On each positive edge of the clock, the T register increments by 1, and as it reaches 9, it resets back to 0, and this implements the BCD counter behavior. So the value stored in T is continuously assigned to the output Q, and this represents the current count value. So the output of this code is a repeating sequence of BCD values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, and so on, with each value appearing on Q on successive clock cycles. To conclude, the BCD counters are essential components in digital systems for counting and displaying decimal numbers. Understanding the structure, operation, advantages, and limitations of BCD counters is crucial for effective circuit design. By leveraging BCD counter, engineers can develop innovative solutions for a wide range of electronic devices and systems. Thank you.